I'd say that like I remember.
Yeah, I know everything about it. I can show you like.
Okay. Let's try to finish moisture analysis. Recap where we left off. What does proximate analysis include? Tina? Ash, moisture, protein, fat. How do we determine carbohydrate? By difference. Okay, very good. What's the difference between moisture content and water activity? Who wants to give that a go? Moisture content, water activity, Sierra? Yeah. Exactly. So moisture content is all the moisture is not chemically bound, whether it's available for reactions or not available for the reaction. And the water activity is the ratio of the pressure of vapor pressure above the sample versus vapor pressure of pure water. And it has to do directly with perishability. And it's only the water that is typically available for changes, chemical reaction, microbial growth, changes. So did we talk about importance of moisture analysis or not yet? Okay, so we're going to talk about it now. What's the importance of moisture analysis? Do you think? And moisture analysis, what does it include? Moisture content and water activity. So when we say moisture analysis, it includes both. Yes, Kristen. Oh, well, Kristen behind you. Yeah.
Determining your perishability and
So perishability is very important. What were you going to say, Graham? I know you're going to.
You told me crazy. I was gonna say shelf life, but she said that. So like
What else? Come up
texture.
with texture. Yes, because well, if a sample loses moisture, it can harden. For example, what can you give me an example of a food product that can harden over time? Yeah. Huh?
Bread.
Bread is one. What else has high protein and can harden? Well, the nutrition bars high in protein hardening over time, because well, you have moisture and moisture in there actually not necessarily due to loss, but to interaction with protein over time. In the presence of water, protein interaction can happen and hardening can happen. Okay, so quality.
Standard of identity.
Standard of identity, yes. I have a feeling we talked about standard. Yeah. So milk, deja vu. I asked you what's the percentage of milk. Yeah? 87. So they add water, it increases the moisture content, and that you can detect standard of identity. So something we didn't say is you actually measure it for nutrition labeling calculations. Because we said although we don't report either ash or moisture on nutrition label, we calculate them because we measure them because we need to get total carbohydrate, which we put on the label, because there's not one method that gives us total carbohydrate content in a complex sample. And oftentimes I feel like I covered this. No? You guys cheated me. and confused me. I already get confused very easily nowadays. Okay, we express on dry basis when we're doing comparison of nutritional component or chemical composition across different types of food. We kind of remove the moisture as a factor when we're doing comparison. All right, did I cover this? No. All right, so the structure of water, without going too much into fundamental chemistry, but there is the water molecules interact with each other via hydrogen bonding. And this interaction is reversible. So you would have association, reassociation, you have dipole moment going on, and that's why when you have a drop of water on the surface, it dries out without heating it. So a food sample can actually gain water and lose water based on the relative humidity of the environment. And the water above the sample in the environment can cause either the sample to pick up that water and have more hydrogen bonding with the water, or make the water leave that food sample and go to the environment. So you don't have to always heat to cause a dissociation of the water from your sample, or the loss of the water from your sample. So because of that characteristic structuring of the water, so we always have this flux of association, dissociation, and interaction with the environment. So when we're measuring moisture content or even water activity, we need to make sure that during sampling and sample preparation and storage, we don't cause changes in moisture content or changes in water activity. We don't want that value to change. So when we prepare the sample, when we store the sample, we try to protect it from losing moisture or gaining moisture. So if you have a very dry sample like Cheerios or potato chips or baby cereal, if you leave your container open while you are weighing out, or even if the TA left it open for you and then 2 hours later the lab start, it's not going to lose moisture, it's going to gain moisture from the environment because it's too dry. So, however, if you open your cheese, your processed cheese or cheddar cheese or Parmesan cheese, they have more moisture than the environment, so you will lose moisture to the environment. So basically, when you prepare your sample for analysis, you want to avoid any loss or gain of moisture that will impact moisture content and water activity of your sample. Okay. For moisture content, so we'll talk about moisture content and then we'll talk about water activity. There are so many methods that you can use to determine moisture content. So this the direct methods and the indirect methods. So the list is huge. Do you need to know all this? No. But you want to know a few examples. Some of them we do in the lab. Mostly you want to know the sample, the methods we perform in the lab. And a little bit about other methods, but not too much. So what we do in the lab is forced draft, vacuum, microwave, and Carl Fisher. So microwave is very fast, but it's not suitable for all types of food products. And we'll talk about that. But another one that is really good if we want a quick measure of moisture is rapid moisture analyzer. So this one, I'll talk about it later, and it's very commonly used when you really want to measure moisture very quick for either quality assessment during production, or even if you're a researcher in the lab and you really want to have a quick idea of your moisture content, you can do a rapid moisture analyzer to do that. In terms of indirect method, refractometer is a common one. Hydrometer is a common one as well. For milk, hydrometer is commonly used. Refractometer, it's an indirect method because it measures total solid. And by knowing the total solid by subtraction, you get the moisture content. NIR, we talked about it last time. If it's calibrated with an official method of analysis, NIR can give you not only the moisture content, but the composition of the sample, fat, protein, ash as well. So there's a list, a huge list. We'll talk about a few. In general, when you do the oven drying method, the simplest and most direct way of measuring and also official methods of analysis, especially the forced draft oven method and the vacuum oven method are most commonly used and official methods for many food products. So basically, you heat the sample, evaporate the non-bound moisture. And then the difference in weight. So all of you have done the lab already. So the difference in weight, you get the original weight. When we say wet weight, is the original weight of the sample with the moisture in it. And then after you take out the sample from the oven, cool it down and weigh it, and subtract the container weight, you get the dry weight of the sample. The difference is the moisture. So moisture content percentage is the difference in weight for moisture content divided by the original weight of the sample. Simple, by 100, you get moisture content. Like I said, often time we do things on dry basis, but for moisture on dry basis might not make sense to you. What does it mean, moisture on dry basis? We need it for calculating isotherm and monolayer. But what it tells you is really the ratio of moisture to solid. That's what it's telling you. It's the ratio of moisture content to solid content. Can it be above 100%? Trick question. Can it be above 100%? Yes, it can. So if you, well, usually we have more than 5 groups for labs. The 6th group, let's say, would be doing processed cheese. Processed cheese has over 50% moisture, 50 to 55% moisture. So when we get the dry basis, moisture contents over 100 because you have more moisture than solid. Okay. So we have to take care of many things when we are determining moisture content. We call this considerations during sample preparation and sample heating. Sometimes we need to pre-dry. So if we want to determine moisture content of milk using an oven method, if we put it in an oven at high temperature, what is going to happen? What happened to the water? Start boiling, and you might have splattering. So the official method of analysis using oven method, forced draft or vacuum, you pre-dry a little bit in a water bath. So you take the weight that you usually like you did in the lab, but instead of putting it directly in the oven, you put it in a water bath around 60 to 70 degrees, evaporate some of the water without reaching that boiling and splattering. And then when it is semi-dry, you put it in the oven. Another thing we need to consider temperature and time combination, because at high temperatures and long time, we induce chemical reactions. Can you name the chemical reactions you talked about in lab that could happen in a forced draft or even a vacuum oven? Go ahead, Sunil. Maillard reaction, yes, absolutely. And is Maillard reaction a condensation reaction, or does it pick up moisture? Does it give out moisture or pick up moisture? It gives. So it's a condensation. So if you have carbohydrate reducing and protein in your sample, and Maillard reaction because of temperature time combination happens, are we underestimating or overestimating? We're overestimating because now the chemically bound water was debound by this reaction, the condensation, and the chemically bound OH and H groups forms H2 oh, and they were evaporated. So now I'm overestimating. I will have less weight at the end, less dry matter at the end because some of the bound water was lost. Okay, great. If oxidation happens, lipid oxidation, will I overestimate or underestimate? Underestimate, because when we have lipid oxidation during pickup of oxygen can happen, and the oxygen becomes chemically bound to the oxidation metabolites. The weight will be added. So the weight of the total solids will be more. So you underestimate the moisture when you determine it by difference. Sometimes we lost volatiles like flavor compounds. Is that caused under or overestimation? Overestimation, because less total solid will remain after some of the volatiles are volatilized, then we overestimate moisture content. So these methods, no matter how you regulate temperature and time, you always have this inaccuracy. It's never perfect. And that's why we call this proximate estimation. So we try to get as close as we can to the actual moisture content in this case. But there's always this advantage and disadvantage. And but we try to minimize it as much as possible. So in vacuum oven, for example, you get less of those chemical reactions because it's at lower temperature, but you get loss of volatiles in vacuum oven. So there is no escaping of potential errors. What could happen to carbohydrate as well at high temperatures? Burn. Yeah, so when you burn, you're kind of like you're burning off some organic matter. So that will cause over or under? Overestimation. Overestimation. All right, so when we prepare our sample, so we control temperature as much as we can, time, and then we choose our containers. So if we choose our containers, we want to make sure that the containers are least reactive with your food product. And if you choose to have a cover, like in here, so if I don't know if you can see from the back, it's like porous. So if you put the cover on top, the moisture can still evaporate, but it will prevent loss of sample. In forced air, especially, you have circulating air. So some samples could be blown away from the container. Another thing that you can use to prevent blowing away is you used in the lab glass wool. So you would put it on top of your sample to prevent that sample from being blown away. Another treatment, if you have samples that could form crust, like cheeses, for example, and if you have a crust, then moisture cannot penetrate. So sometimes forming that crust is undesirable. You don't want it. Otherwise, moisture will not evaporate and you underestimate moisture content. So they put special clean sand in the pan and mix it really well to avoid clustering of the sample and forming crust at high temperature. Okay, so all of this will help you when you're trying to formulate and look at your data and determine why some methods are better than other methods. Based on the data you collect, you can think about those issues. So particle size is very important. If you don't have small particle size, you won't have enough surface area for moisture to evaporate. So it's always good to reduce the surface, the particle size to enhance surface area. Amount of volatile compound will cause sources of error no matter what you do, whether it's vacuum or forced draft oven, you're going to lose these volatiles. So you want to keep that in mind. You want to make sure your temperature time combination is not too high. In this figure, you can see at higher temperature, you lose more water than actually present in the sample. And that's due to loss of chemically bound water. We talked about lipid oxidation. Some samples are very hygroscopic. So let's say sample high in lactose. Really would like to keep that water, doesn't want to give it up. It's very, very hard to spray dry, for example, if you talk to Mitch or Ray in the pilot plant. Spray drying high lactose solutions really hard because of the wanting to keep the water bound, hygroscopic. Like I said, burning of carbohydrates, surface crust formation, splattering. That's why we do that pre-drying, and improper storage. You put your sample back in the desiccator, right? And then when you put it in the oven tomorrow, someone's going to take it out and put it in a desiccator to cool down. The desiccator, it had, what did it have? What are these called? Desiccants. So was it blue or pink in color? Did you remember? Don't know. It should be blue. Pink in indication of saturation with moisture. So you put it in desiccator. If your desiccant is already saturated with moisture, your sample after drying is going to gain moisture from the environment, even in the desiccator. So we need to make sure that it is stored properly in a desiccator that has dry desiccant to ensure that the sample maintains its weight, goes down to room temperature so that you can weigh it after drying tomorrow when you come to lab. Some of you already weighed yours. Okay. Any questions? You can interrupt me if you have questions. Remember that? Yes.
For the oven drying, how confident are we that we're like getting all the moisture out?
Yes, that's a good question. So Tyler is like, how can we be confident? So usually we follow official method of analysis, following the temperature time combination suggested by the method. And how did this method became official is by trying and validating it many times across different labs. And then they figured out the combination. Yeah. And usually what you do is, how they validate is they put the sample in a different temperature time combination and take it out after intervals of time until constant weight is reached. Yeah. So vacuum oven is also an official method of analysis. Oh, did I skip this? I skipped this. So we have very many official methods of analysis for forced draft for different types of food. Every food has its own method. Some have similarities and some are specific for the type of food. High in carbohydrate, high in lipid, a mixture of all. So they will give you specifications. The AOAC method and the AACI method methods. I think they are still called AACCI, although they changed to cereal and grain, the association, right? But I think the methods are still called like that. Yeah. Okay. So in forced draft oven with the name forced, so your air is circulating and the hot air is circulating. This means that wherever you put your sample in this oven, they're all getting the same heat. So there are not like one that is closer to the side is getting more hot than the one in the middle, than the one further from the side. So even circulation, which is an advantage, basically. So you should have very low coefficient of variation. If you did well in weighing and you put your samples in different places in the oven, it shouldn't impact the precision of the method. Simple, you weigh, you put it in. Disadvantages, volatile compounds may evaporate. High temperature time combination cause chemical reactions, splattering for liquid samples, and powders blown away. And that's why we have precautions for all of these disadvantages, with the exception if you have volatiles, there's not much you can do about it. And sometimes you do get chemical reaction despite your temperature time combination adjustments. Vacuum oven also, it's an official method of analysis. There are very many for different types of food. And the advantages of vacuum over forced draft is that you have lower temperature. So you reduce the boiling point of moisture, so you evaporate at lower temperature. So you have less chances of burning of carbohydrates or Maillard reactions and other chemical reactions that are sped by heat. So this is a good thing. However, one of its disadvantages is you don't have really heat circulation. You don't have a fan in there. So sometimes you have uneven distribution of heat, which might cause lower precision than the other oven. You will still lose volatiles. There's no way around it. And then another thing, and depending on the vacuum oven we have, there are different types of water traps, or they call them sometimes cold fingers. Have you heard of the term cold finger? It's an old term, but basically when water, there is inside of the oven, there's a place for water to escape. And then when it's escaping, you collect that water in a moisture trap. Did you see that in the lab? Did you see? Yeah. And was there a desiccant in it? Yeah. So the desiccant in it collects that moisture that in a form of vapor, and when it comes to room temperature and regular pressure, it condenses and gets collected before it gets to the pump. So you're trapping moisture before it gets to the pump. What's the pump role here? What is pump doing? Generating the vacuum. So you're generating the vacuum that is pulling the moisture off of your sample, but you don't want that moisture to get to the pump and ruin the pump. So you have this cold trap, it's cold under room temperature, basically, condensing the water onto the desiccant before it gets to your pump. That's why it's called cold finger, just condensing the water. Okay, microwave. So you've done microwave already. It's very quick, takes few minutes. Depends on the type of sample. It might take a little less time or more time, depending on the type of sample you have. It is not really suitable for high carbohydrate food because of burning. Did you get burning in Cheerios and baby cereal? Did you notice any burning? No? Oh, wow. That's cool. But we'll see how the data looks like. Okay. But when you put your sample in the pan, it has to be uniform and centered. Any changes in the thickness of the sample between one rep and the other will cause erroneous results or not as precise results. There are few official methods, not for every type of food. There are for tomato sauce, meat, and poultry products, there are official methods of analysis. In the pilot plant, it's mostly used for dairy products, and it's calibrated for dairy. So infrared drying, that's fast, rapid for quality type of testing, not an official method of testing. So infrared causes heat generation, and you lose moisture, and then it automatically takes the weight before the heating and after the heating, and you determine moisture content. You get a read up directly. Rapid moisture analyzer, similar thing. You have heating, halogen heaters, and then you also put your sample, and it takes few minutes just to get a reading. Evaporate, you heat your sample, evaporate, and then you take measurements before and after. And again, this is not the most accurate, but it's rapid and gives you an answer right away of an approximate moisture content in your sample. So there are other methods. Distillation method is one where you heat your sample, and then with toluene and water, they're both immiscible liquid. So the water is not miscible with toluene. So they get evaporated and then distilled, and you collect the distill from here. And then you measure the volume of the water removed because they separate. Now, Carl Fisher you did in the lab. It's a titration method. It's usually the official method of analysis for low moisture food. Why? Those you did the lab. Why do you think this method is good for low moisture food? It's going to give you good results for cheese as well. Yes, yeah. Yes. Yes, it takes longer time to titrate, use more reagents. So it's not really efficient when your moisture content is high. It's good for dry food and also low fat. Why low fat? Because one of the reagents
React with like unsaturated fat.
the iodine, because you have iodine in there. It reacts with double bonds, and then you overestimate water because the reaction is based on the reduction of iodine by SO2 in the presence of water. If you have unsaturated fat and high amount of that, the iodine will be reduced by the unsaturated fat, and then you get overestimation of the water. So methanol is the solvent that you used in the lab. We extracted with methanol, so sample was extracted with methanol for you ahead of lab. So the water moves into the methanol layer. And we use methanol as blank to correct for any moisture content in methanol. And then we titrate, and then you measure the volume of the titrant, and you use that to calculate moisture. So all of you done that in the lab. And we do have to calculate Carl Fisher reagent, KFR value, which is basically determining how much reagent is needed, or how much the value for water reacting with 1 milliliter of KFR. And you use that to calculate the amount of water. So you determine 1 milliliter of KFR, how much water is needed for that. So you do standardization. You can standardize with pure water or water in methanol standard. What did you use in the lab? Methanol? Yeah, okay. And there are old units where it's manual, but most of the units nowadays are automated. The one they used in the lab is automated titration. And now we go into those methods that I'm not gonna go into detail or request you to know very much details, but a few of the physical methods. One is based on measuring the dielectric or the electric current you pass through the sample and through water. And then you do standard curves. So for example, dielectric constant of water has a specific value. So that's all what I want you to know. Other physical methods. the hydrometers, so it is based on measuring specific gravity, so the displacement. And then the other one is the pycnometer. I can't even say the word. But basically both is based on determining difference in specific gravity. For example, so the pycnometer, you take the weight of equal volumes. It's for liquid samples. So they take the weight of equal volumes, and then you calculate the specific gravity based on that, and then you use charts to convert to moisture. Refractometer is very common. We use it a lot in the pilot plant, actually, not only to determine moisture content. Let's say we are trying to get desalting we're preparing protein ingredients at the end before going into spray drying. We want to remove the extra salt. So it goes through membrane filtration. We call ultrafiltration, diafiltration. We use this refractometer to determine the total solids, and we keep filtering and diafiltering until the permeate that comes through the membrane has 0 reading for refractometer. So basically, it's mostly water that is coming up. So it's an indirect method of determining water content by determining total solids. Freezing point is another common method for moisture content. And you know, when you have pure water, it freezes at a particular temperature, 0 degrees Celsius. And the more solids you have in there, the temperature of freezing goes down. So freezes at lower temperature. So you use that with charts to calculate moisture content. It's usually used for milk to detect addition of water. So you have table 15.5 to compare and contrast. So focus on those methods that we did in the lab. Okay, so we did 4 methods in the lab for moisture content. So make sure you focus on those and compare and contrast. Any questions on moisture content before diving into water? Okay. So water activity is important for quality and safety. So quality, because water activity affects texture. So texture is important. And also spoilage microorganisms, color, flavor. So quality is important. So anything that impact or affect chemical reactions or cause chemical reactions, enzymatic reactions, or microbial growth is related to quality. And for microbial growth, you have spoilage versus health concerns, safety concerns. So you have the pathogen growth and the spoilage microorganism growth. Okay. So this is a very effective diagram for you to study and understand the impact of water activity on different chemical reactions and also microbial growth. This is a figure by Ted LaRusa, our famous Ted LaRusa. We call him the godfather of the water activity. He even had his car license plate says water activity. Yeah, he had a ship that is called water activity, fishing ship. So anyway, he was quite a character. I'm sorry you missed having him guest lecture at least. He used to torment the students, by the way. He would ask a question and take out $20 bill and ask an impossible question to answer. And then he would say, if anybody answers, we'll get the $20 bill. Of course, nobody answers. I don't know if he even knows the answer. And then he puts back the $20 bill in his pocket. That's a famous famous thing that he would do. Anyway, so it shows here dry foods, intermediate moisture food, and then high moisture food. So, and then the y-axis shows the increase in the reaction rate. And then here you have the water activity on the x. So x-axis water activity, increase reaction rate on y-axis. So you need to orientate yourself. And then you have those three colored lines. So you have lipid oxidation in blue. You have Maillard browning in brown. And then you have a microbial growth in yellow. So, and then you have the changes in physical properties. So as water activity increases, look at glass transition. Do you know what glass transition? TG. What does it stand for? Who's going to be a brave soul? Go ahead, Mitchell. Yeah, so what happens above the TG? Above the TG, when you go above the TG, you get a little bit change in molecular mobility. So you go from glassy state to amorphous state. Yeah, so when you pass the glass transition, it becomes more rubbery, from glassy to rubbery. Oh, so this is what this T, the temperature below glass transition, much lower and much higher. So it's kind of giving you a relationship of moisture, glass transition. So think about, just to put things in perspective a little bit, think about when you have flour and you add water. What are you making? You're making a dough. How do you make the dough? You knead it, right? You're kneading and you're forming the dough. So what are you doing to the gluten? It's going from a glassy stage to amorphous stage. So you have to have a specific moisture content and temperature to go from a glassy state to amorphous state and get that viscoelastic properties of gluten. So that's one example where temperature, moisture play important role in gas transition. So you go for certain properties. So when you have low water activity and let's say you have a powder, so the powder becomes cakey, so it sticks to each other and cakes. If you have a potato chips, it's going to be less crispy, okay? And then if you have a specific water activity and actually you're losing moisture and the water activity is going down, you get hardening effects. So yeah, and then here it shows you, for example, Maillard browning, maximum is between 0.6 and 0.7. You get highest activity. And then at very high moisture content, above 0.8, 0.85 to 0.95, you start getting those microbial growth happening, spoilage, and pathogens. So this is also taken from Labuza's book on water activity. It really shows different products. And you heard of the monolayer? So what is the monolayer? Yes, from the image, try to guess. Yes. So, and the product is the most stable. Yes. So the highest shelf life you have at the monolayer, where the water activity is low enough. For different products, we have different monolayers. So we used to have a lab where we actually calculate monolayer, plot isotherms. This is an isotherm. You plot an isotherm and determine the monolayer of the food samples. to determine at which water activity they have the highest shelf life. So here you have different products. So it shows you a different moisture content. For example, when you have water on dry basis, so 1 gram of water per 1 gram of solid, that means you have a 50% moisture. It shows you where you have bacterial pathogen starting to grow. Down here at the monolayer for potato chips, above it we lose crispiness and so on. So it is just an image that you want to orientate yourself for your own information to see how changes in moisture and water activity impact the stability of the product. Okay. So mostly food products have monolayer between 0.2 to 0.3, and that's where it's most stable. Above that, if you have a potato chips, you lose crispiness. And for some sugary powders, become sticky. Or if other powders like baby formulas, they become, they cake. And then you get hardening upon water loss for soft material, for example, raisins and marshmallow. And then 0.6, you start having microbial growth between 0.7 and 0.8 maximal rate for chemical reactions. And then above 0.85, you start getting pathogen growth. And then much higher, very rapid spoilage happening at very high. What's the, let's not water activity, what's the moisture content of cucumbers? 90 plus, up to 95 even. What's holding the cucumber together? The fiber. So it gives you that really crispy texture, but it's mostly water. If you put cucumber less than a day out, it's gonna have to spoil. Okay. So water activity, let me finish this in 2 minutes. You're measuring, we talked about that. You're measuring at equilibrium the moisture vapor, or the pressure of the moisture vapor, partial pressure of moisture vapor over the pressure of pure water. So we talked about that. So you only measure water activity, you try to measure it if you at least plot an isotope when you have equilibrium. So you want to make sure that your samples are put in a desiccator, they are equilibrated at a particular water activity, and then you can get the equilibrated relative humidity of the sample. So need to control the container size, amount of sample, time, temperature, sensor calibration. So we have different methods. One is based on dew point. Most other common one is based on measuring electrical difference. So what you did in the lab, I think, is the decagon, which is based on the dew point, correct? So yeah, just remember that, the principle of that method. The other one that is really common is the electric hygrometer. We don't have one, but these are two different methods. I don't want you to worry about the one that you didn't do in the lab. Just remember what Brittany and Charu went over depending on your lab group. It's a dew point analyzer. This is a table, FYI, the range of water activity in different food products. This is a good table to just, if you get asked to give me an example when you use which method, only focus on the ones we did in the lab. Okay. I thought I would be done. I'll save the isotherm it'll take a minute, but I'll save it till Friday. Okay, yes.
Yeah.
Go saunter away. It's like you're. You know what? You have to go to work. I have to go to work. Oh, okay.
Yeah. And then like that, I'm not overpowering like whack. I was
It's like.
All right, I might just email Nadia to let her know. Okay. Thanks for coming. I definitely need that.
Where should I leave it? Oh, you want to meet at my office? 146 first floor. Yeah, you know where that is? My library. Same here, right? Yeah, all right.
I do not have credit. Oh, okay, before I'm not in.
Okay, sorry. Let me stop sharing.
Right.